Hello, today I'd like to talk about my HDL workflow so that maybe some of you watching this will learn something from it and maybe implement some of the methods that I use in your own workflows. So I'll be breaking down this talk into four sections. The first section is the use of a snippet engine in the editor that I'm using, which is Neovim, and how that makes it easier for me to type stuff faster. And the linter, which is basically also how we can make sure that the code that we write has no errors, the sort of things that you expect to see in most, like in VS Code, when you type in Python, all these sorts of things. So yeah, but we would like to have that facility also to things like Verilog or VHDL. And then how do you make sure that your design is functionally correct through simulation? And then finally, that your design is synthesizable. So let's start maybe by going first of all through this part, the snippet engine. Now let's take for example something like this simple one. So let's ignore this for now. So snippets basically just means okay, let's not ignore it for now. So basically this is a very simple design which shows you how to implement a generic counter in system Verilog. So usually, I mean, this is very simple stuff. This is something that you can type yourself line by line. There's no big deal. But most of these things, like let's say you haven't used System Verilog for a while, or let's say you don't simply want to type, you don't have the desire to type any of these things. One of the ways you can avoid all of this stuff is you simply want to design. You don't want to be bothered with remembering all of how whether you need to put a comma here or no comma here, or these sorts of things. So this is where something like a snippets come in. Now, probably lots of you have used snippets in your previously in your life before, and they really work well. I mean, most snippets. I mean, basically the snippets that I'm going to be showing you here are just your regular type of snippet, but they have more power. So usually when you use snippets in things like VS Code, you would just say, okay, if I type the word MOD, it will paste some predefined set of text. However, in my case here, since I'm using something called this thing here called LuaSnip, it's a snippet engine that is built specifically for Neovim, and this snippet engine is extremely powerful. But of course, it's extremely powerful, but it comes at the cost of being a bit difficult maybe to use. But since this video is not about discussing how to use LuaSnip, all of these sorts of things, it's just to demonstrate that yes, with LuaSnip you can write very extremely powerful snippets. The sort of snippets that can be dynamically updated, the sort of snippets that will paste some text based on certain conditions, whether they are met or not, and these sorts of things. So let me just maybe demonstrate a few things for now. So let's ignore this part for now. So usually, as I said, when you have a Verilog system Verilog, let's say file or a Verilog file, you type with something like a module, something like that. Now, so I type module, for example. I do this, like I expand the snippet with some keys on my keyboard, and it gives me something like this. Now, so far, this looks like this sort of snippet that you might get with any sort of other snippet engines. Now here I can type, for example, the name of the whatever my design or something like that. Anyway, so then I go. So now this is where LuaSnippet actually starts showing its true colors. Like it's really powerful. So here I can now whenever it shows me this yellow dot or whatever, it's telling me that this is an option node. It means that I can turn on something or turn it off. So as you can see, I can press something, I can then turn it on, and then here it tells me that okay, so now with system Verilog modules, if you have let's say parameters to the module itself, these are like generics in VHDL. So these are the sort of things that you sometimes might have or might not have. So that's why these are options here. So similarly, what you're seeing currently, my cursor is inside this place here. This is asking me for the ports. So usually, if you have a regular module, you would definitely have ports for the module. But if you have something like a module for a test bench, there is no need for something like this. So you can cycle between these different states. So let me show you for the first one. So as you can see here, it has pasted for me a couple of let's say ports and these sorts of things, so that if I have forgotten how to, let's say, for somehow I have forgotten how to write all of these things, I will remember, okay, so to define something like a single bit input, it's input logic CLK or whatever, and then here it takes me now finally to the implementation details where I can implement my design or something like that, and then finally I'm done. So as you can see, just with a few lines of code, I have just generated something which is very easy to see. Again, just type it something like this. Now in this case, let's say I don't want a generic, so I just go do something like that. I just do this, I'm done. So you might be asking, like, why didn't I remove this part? Because it's System Verilog requires, whether it has ports or no ports, to always have brackets. So anyway, so just between the two. Now the nice thing about all of this is that the generation of this one and the generation of this one is done with only a single snippet, a single trigger that I have to remember. So I just have to remember module. Now this, what I've just shown you, can actually be achieved using other snippet engines. But with other snippet engines, you will have to write two different snippets. Each snippet will be associated with a different name. Like, for example, this one you will call it maybe regular module, module 1, or maybe this one module 2. So when you have to expand this, you have to remember, oh, do I want the module that is called module 1? Do I want the module which is called module 2, or something like that? Whereas if let's say a few months go by, and then you can't remember anymore whether you had defined this snippet to be module 1, or the only thing that you remember in your head is that this is something called a module. So this is why I find it, because in the other snippet engines that I used to use in the past, I would do something like this, where I would break the snippet into two different snippets, and then after some time goes by, I come back and I suddenly can't remember anymore the triggers that I had defined for the snippets. And then, yeah, the snippets become less useful than, or maybe I will have to look at the snippets. Have a look at the file, and then, it's just less useful this way. So anyway, this is a very, very simple one that you can see. I will probably go through a few of them very quickly, so that just to give you a feel. So another very common thing that you do in System Verilog is to have always blocks. So again, always. So you can see I do something like that. So this always block will always this is just to help you, let's say, write code quickly, even though this might not be exactly what you want, but at least it puts for you the blueprint of how you can modify it to fit your own needs. So as you can see here, we have a clock, we have a reset. Maybe you don't like the way of the name the reset is currently called, so I can just give it reset. Notice that when I type reset, this part here will be updated similarly, and then it tells me what's the reset logic. I can do whatever, do here whatever, and then I'm done. So this is for the always block. Now again, if you remember, if you notice here, there was this same yellow dot. This same yellow dot means that this whole snippet has options. Has alternatives. So I can press this one. So you can see this is the always combinatorial block, which is how you can represent one way of doing combinatorial logic. And then another one, if you want a latch, you can do something like that. So you can flip between them quickly just with one single keyword, and then just like that. Again, some other thing that you might do, for example, a case statement. These things are really case statement. For me personally, since I use more than one programming language, for some reason I cannot always remember, like, does this have a comma, a colon here, it has no colon here, or do we always have to include the begin statement or no begin statement, these sorts of things. So I just press case. Again, it goes through the same thing. So it gives me some, some comments reminding me, okay, this value, this is the case item, which means that it's a specific case of this, and this is the default and all of that. Now notice it also shows, it's telling me that there's an option. Notice the option is that you can press this. Then it surrounds this thing for me with an always combinatorial block. This is because case statements should always be enclosed inside combinatorial blocks. But it's possible that, let's say, I was actually typing this thing here. Let's say I had some combinatorial block already that it was inside. Yeah, so something like that. Let's say I had another combinatorial block. I would simply type, say, case, and then there is no need for me to, for example, include the combinatorial block twice, because this would just duplicate it for me. You get the point. So yeah, so this is a case statement. And then another thing that you probably would like to write is the if statement. So if gives you the condition, blah blah blah. It takes you to the other one. Now here you say, okay, I want an else if. Again, you just do this, an else if block. Then you type your else if. Then you do another one. You type whatever you're supposed to type for the else if statement. Then you come. Do you want another else if block? Why not? Let's do another else if block. Another else if block. Why not? Yes, another one. Finally, say, okay, you know what? Let's put an else. So else if, then I can switch between them. Else, I'm done. So just like that, I've just generated the set of a blueprint for a bunch of else if statements, and then populated them for me with the begin and end blocks and all these sorts of things. So what else can I do I know of head I can do? Of course, FSMs. If you're trying to build FSM, there's usually a template that you have to follow. So all I have to do is do an FSM. As you can see, I mean, this is very straightforward. There's no like magic going on here. So basically it just pastes for me like, okay, this is how you do an FSM. You define the state encoding, then it's the state register. How do you do next state logic and the output logic and all these sorts of things? So basically I can then look at this. I say, oh, okay, now I remember how to do FSMs. Yeah, so basically I just do this edits and then I am done. Another thing that we can do, okay, you know this thing called this the ternary operator, which can be used to implement things like a mux to, like, for example, I can do assign maybe a signal is equal to if certain condition, whatever the condition. Let's say this is the condition, and then you put something like that, and then you put something like this. You get this. You get the point. So which means that you will assign this signal S to this value if this condition is true, else do this, something like that. So basically, how do you do this? You do it with something. It's called ternary. Then I do something like that. I get it. So the condition, I type the condition, value if true, and so on and so forth. Now it's also possible to, if the condition is true, then maybe you want to do another test. Or if the condition is false, maybe you do another test. Then inside this you do another test. You get the point. You can nest this ternary operators with ternary operators. So basically you can do something like this, ternary, then you say 2. You can see this, condition 2. This means, I mean, condition, the outside condition 2. This, if this is correct, then do another test. Based on this test, you do something like this. If this is wrong, then do this thing again. So actually, this is really one of the things, this is probably one of those things which you cannot do with other snippets, to generate snippets on the fly. Let's do this, for example. You want ternary 4, as you can see, it generates for you 4 conditions. It generates for you. So basically, it responds to all of these things. Now, I also use this a lot when I'm using LaTeX to generate for me tables. I can just specify, like, I want a table of this size, it generates it for me, or a matrix, or all of these sorts of things. Anyway, you get the point. So in fact, there are lots of other things that we can do. For example, let's say I want a binary counter, so I just put a B counter or something like that. Then I can do just like that. I have generated a binary counter. I want a what's it called? I don't know. I can't remember everything off head right now. But let me show you the system Verilog, how exactly it's done. Because right now I've just shown you what it's doing, but not how it's done. So basically, so this is my file. This is again this tool that I just showed you. This one, Lua snip. This is how you define your snippets inside Lua snips. Lua snip. So basically, let's say for the module. So let me show you. So remember this thing that we just did just now. This one, this module, this one. Yeah. So this is basically how I'm doing it. So I come inside the module. I see this is the trigger. So which means that this is what I type to generate for me the module. I didn't bother to put the description because why not? I mean, why do again? So the module, as I said, if you haven't read anything about, if you've done other snippet, if you've used other snippet engines in the past, this will probably look like it's a bit strange because, as I said, Lua snip is super powerful, but it comes at the cost. The cost is it's not as straightforward to use as other types of snippet engines. But once you get a hang of it, of how to use it, suddenly you realize that there's nothing you cannot do. I mean, like this T, so this T is a text node. So which means that insert for me a text with module. So let me just demonstrate. You see this thing module with a space. So this is the text node. I is an insert node. It means that when you let me this module. You see when I do this. So this insert node, it's node 1. It means that's the first stop. The first stop. It means the first stop. Ask the user to change this thing. Then another text node, which is a space, and then here we use a choice. So you remember previously I said you can choose between either to have a, what's it called? A parameter or a generic or not. So this is a choice node. Choice node is located at position 2, and then it can choose between either nothing or either another snippet node. So this SN is basically something like that. So inside this snippet node, you can have all of these parameters and so on and so forth. I'm not going to bother you with the rest of the details, but this is basically how I do. And then how do you instantiate a module, the if statement, case statement, ternary, FSM, for generate. And then for the other things that I was doing, like this logic blocks, let me show you quickly. So logic blocks, how do you generate a priority encoder, decoder, binary counter, all these sorts of things. So let's say you want an RAM. So basically you do something like that. I mean RAM, then you do it like this. Suddenly you have your RAM, and then there. Basically that's it. So this is how I do my typing in of system Verilog inside what's it called, inside the Neovim. Of course, I have things for like no, not here. Like for example, system Verilog, you can see I have other things like other snippets that I've written in the past, like for VHDL, for LaTeX, and all these sorts of things. Again, it's the same way. Basically, after you've written a few of these, you realize that most other languages are almost the same. So you just copy paste your snippets and then you modify them slightly, and then you're done basically. So the next thing I want to talk about is, okay, the linter. How do I do linting in how do you call it? In Neovim. Very good. So this is my original file that I had written. I showed you previously. How do we implement a binary counter? So this is a binary counter, that very simple one. So as you might imagine, when you have a much more complicated file like this, it's very possible sometimes you forget a semicolon here. I mean, a semicolon here. You forget to type maybe a comma here or something like that. You get the point. You have some syntax error. So previously in the past, when I used to, I mean, not do all of the, I mean, back in those days when I used to, just started learning HDL and it wasn't as computer savvy as I am now, I would just use something like Notepad++, write all of this thing, take it to, let's say, Model Sim or whatever, and then start doing compile. It gives me an error. I come to the code, I change it, I go back there, and it's a long, boring process. So of course, if you use something like VS Code or whatever, and use a language like Python, you always have these things which will automatically tell you whether you have an error in the code or not. But this is not the same when you have very niche languages like Verilog or VHDL. These are something that probably you either have a specific editor that takes care of that for you, or you have to do it yourself. So let me just show you quickly so that it's more concrete. So let's say, for example, here I forget this one here. So obviously the syntax highlighting obviously helps. I mean, but this is not this does not say that the code is, because the syntax highlighting, somebody had written some regex code that will highlight this whole file in a way that it's supposed to reflect valid system Verilog code. But this is by no means like a correct code. I mean, this by no means is supposed to be an equivalent to actually performing a linting of the code. But let me just show you. So when I save it like that, you can see I save this, I can see an error here. So this error is telling me near parameter, syntax error, unexpected parameter near this. So now I know that I have an error around this point, so I can correct it. So something like that. Let's say I do another one like this. You see, it tells me that I have an error here, whatever. So let's say, for example, instead of count, I have aunt or whatever. You can see on identify variable aunt. So how am I doing this? First of all, I am using a regular VHDL or system Verilog simulator tool. Like if you're using GHDL or Icarus or Model Sim or whatever, so that it's easy to explain what I'm doing, let me come to this part, the counter. So you remember, let me first of all change this so that we can see what exactly is going on. So you see this part? Let's change it and do something like that. Now this is this file one more time so that we can see. Let me just do it one more time. Okay. So this is this file again, same file. You can see where we had introduced the mistake. Now I can do something like this, maybe zoom in so that we can see. Then I can do vlog. So basically you see the command that, let's say you do not have Neovim, all of this fancy stuff that I have. So basically this is the way you would check if the syntax is correct. You would do a linting, And then as you can see, it tells you exactly that error, the name of the file, the line, this is the code, the error code, which you can check in the manual to know what it means, undefined variable. So basically this error that you see here is exactly the error that we're seeing here, undefined variable, whatever. So basically, usually when you have some fancy linters and these things for Python or whatever, they are usually called language servers. So language servers, they are written, it's basically something like, I mean, this Verilog that you see here, it's the binary of the Verilog compiler, which is for this specific tool that I'm using. So usually when you have these fancy language servers that are used for things like Python or whatever, you can how do I say, not automatically, but you can directly talk to them, and the language server will send you the result directly. However, in my case here, I am actually not using the tool as a language server. I'm basically asking the tool to like compile the file for me or whatever, and then print out the output. And then this is the output that I'm going to actually pass so that I can know whether it's an error or not error. So based on the type of output. Of course, this is not a very, how do you call it? It's not a very efficient way of talking to servers or whatever, or language servers, but who cares, because I'm only doing it once during save. Notice, it's only during save. So if every time I save, I call this once, I don't need to be while typing these receiving errors. I know for sure that the sentence is not complete, so I don't need the tool to be reminding me every second that, oh, you have a fault, you have a problem. So the way I do this, let me show you quickly. Okay, before I explain this, Neovim has lots of plugins. One of the plugins that it has, it's called null ls or something like that. Now null ls has all of the boilerplate code that allows you to send it information about the line in the code which is giving you an error, and then it will display the result here. That's basically it. But how you pass this file is something that you have to do yourself. So let me show you quickly what I mean, because sometimes when I say things, they sound much more complicated than they are. So let's go to null ls. So this is null ls. I'm going to show you. So this is when I'm using this. So inside null ls, I just have to tell it that this is the, how do you call it? This is the file that you are supposed to use for this Verilog parsing, and this file is located here. And then this is just basically boilerplate code that you just copy paste, and then you just say, okay, use this for now. But let me show you what's inside this file, because this is where, let's say, all of the heavy lifting is done. You go to null ls, built-ins, diagnostics, and then vlog. So this is how it looks like. So we have a normal, so this is basically the boilerplate code that you get from null ls. It tells you that, okay, I'm going to call this thing for vlog, and then it's going to do the diagnostics on save when I save the file, and it's going to apply to files of Verilog and system Verilog. And then this is, remember this command that I was writing here, blah blah blah, I write it here again. So args quiet lint walk, and then the file name, then boilerplate code, and then it tells you how do you pass the output. So I mean, how do you know about the output? See, I'm going to pass the output, and it's a raw file. Then you write your simple function. So this function, this params here will be the output from this, let's say for the output from this guy. So you capture it, you split it into lines, then you do some regular expressions. You say, if I have this type of regular expression, this is capture, put for me this value here into severity, this into this, blah blah blah. So I'm testing here for two different types of messaging that I'm getting, and then if I'm able to match the output, which means that I have some error that I'm looking for, then I take it into this. You see this guy called this done. So basically done is the function which you have to pass the diagnostics which get displayed inside Neovim. Then I just insert the row number, code, whatever, and then if the severity that I got from this, for example, you can see here it's error. If it's error, then put as error. If it's warning, do warning, because error will be displayed with a red color and warning will be displayed with a yellow color and stuff like that. So basically, okay, I shouldn't be doing this. So let's go back to this and then see here. So yeah, so this is, where is it? Yeah, back one more time. So let's say do something like this. You see we get the errors that we expected. So basically this is how I do linting inside Neovim. As you can see, so fast way of typing code with snippets, linting, which allows me to verify that what I'm typing actually is syntactically correct. And then the third part is to make sure that the code itself that I am doing is, this part is to simulate. So which means that, okay, I have implemented some functionality. I'm sure that the code is actually syntactically correct, but is it functionally correct? So this is where you have to write a test bench. Now, if you are like me, I actually enjoy writing VHDL or Verilog or whatever. But if there's one thing I hate doing is actually writing test benches, because they're so verbose. They're just irritating to write. So what I've decided to do is I'm not going to use system Verilog to write test benches at all. So I'm going to use this a way, this is called CocoTB. It's a way where, so because at the end of the day, you've designed your module in VHDL. How you test it has nothing to do with VHDL or Verilog, to be honest. I mean, if there's no reason to the way you test it, you have to test it in VHDL or Verilog, because VHDL and Verilog are supposed to describe the functionality of hardware circuits so that the synthesis tool can produce that hardware for you. At least if you are using VHDL and Verilog for the purpose of producing synthesizable circuits, which is basically what I'm using them for. Then at the end of the day, once you have this synthesizable circuit, how you inject input, test inputs, and all these sorts of things are supposed to be used. You are supposed to be doing them in whatever way you want. So one of the ways that you can do that with Python, if you're already familiar with Python, then there's no need for you to go through all of that mess that you see, like how do you write classes inside system Verilog and all of these sorts of things, and then you go through the whole, I don't know, very complicated, very complicated process. So to give you an idea of how I go about doing this, probably lots of you who are watching this video have not probably even heard of CocoTB. Probably most of you watching this video used to write, just like me, some time back, system Verilog or VHDL test benches in the actual language that the design was done in. And then you would go through a very boring process of maybe trying to see, okay man, should I put this input as this? Should I do this? Should I change the input to this? How about if I want to test the circuit under these other circumstances? Suppose I have a generic circuit, I would like to test it for this amount. I would like to test it for this bit width. I would like to test it for this bit width, and all of a sudden you realize, oh my god, I'm in a complete mess. So let me just maybe go through one example. Maybe you can see like the flow that I have. So let's see. So this is why I use this file from the get-go. So here I have a binary counter. So a binary counter, as we know, it simply counts +1, +1, +1, +1, +1, as long as you give it a clock, the rising edge of the clock or whatever. So let me show you. So this is basically how I would write a test bench for this inside CocoTB. So no, this is not the one. That's the wrong Y. So this is the test file. So let's focus here a little bit. See this part. Let's have a look here. Yeah. So this is an async. So with CocoTB, let's forget about what async means for now. Just think of this as just a regular function. So this is basically the test. How we're going to test the circuit. I'm going to first of all generate a clock, of course. Think about it the same way as you would write your test benches in VHDL or Verilog, but instead of having to write them in VHDL or Verilog, you now have Python. So what's the big deal about the whole of this? The big deal is that if you're already familiar with Python, you don't need to learn some other new language, some other very complicated language. That's one. Two is Python already comes with a huge amount of libraries. So let's say, for example, you are designing a FFT, a circuit that computes the FFT of some signal in hardware. Now you would like to test this circuit with actual, like you have to say, okay, if I give it this input, this is the actual output that I'm supposed to get. The question is, how do you generate golden input-output pairs? Now you say, of course, I will just write the code itself that generates the code that takes an input and produces the FFT of that input. And then, of course, now you start thinking, oh, I have to implement FFT in system Verilog or in VHDL. I start thinking, oh shit, I have never probably even implemented FFT in my life. So now I have to implement. Of course, maybe somebody else has written FFT, but you get the point. You have to really implement it in that language. Whereas when it comes to something like Python, you already have NumPy, and you probably use FFT in your life a million times. So you just do import NumPy, whatever, and then you use the FFT function inside NumPy or SciPy or whatever, and then you generate a bunch of input-output pairs just with a single line of code. Of course, you might be saying, yeah, but just so that we are clear here, what you are generating is just test input and test output. This has nothing to do with hardware. So whether you use NumPy or whether you use whatever, it doesn't matter, because all you're generating is input-output pairs. Just so that we are clear here about what exactly I'm talking about. So we have, we generate my input clock again, my reset logic, yes. So because of course you have to reset this thing so before it works, and then everything here is written in a generic way. So based on the, okay, probably I should explain a bit so that I'm not confusing people here. So first of all, we generate the clock. How do we generate the clock? Again, these are sort of stuff that you just have to go through the CocoTB getting started, and it just tells you. It's really, really simple. The sort of, I mean, you can go through this probably in, let's say, 15 minutes, maybe, and get a grasp of how to write test benches in this. So let's have a look. So here we see, we create a clock. So so this thing called DUT, it means the device on the test. To access the signal of the device, you say DUT dot the name of the signal. That's it, basically. And then you give it a period, and then you tell it, I want the period in nanoseconds or whatever, and then whether you want to start the clock now or whatever. Then again, for something like the reset logic, remember, forget about all of this. These are just like boilerplate. These are just like extra stuff that you write because you can do it. So basically, this is how you take the signal. So again, DUT, notice here. So DUT is the device on the test. The name of the reset port is rst.n, and then I would like to access its value, so which means dot value, and then I would like to set its value to some number, and this number you can get it from here or here, and then I would like to make the reset happen after, to hold this value for 1 clock period. So you say maybe if you want 2 clock periods, you just do something like this, or 5 clock periods or whatever. You get the point. You come to this point, you say, oh, wait for, if you've used VHDL, that's basically what you say, wait for falling edge of the clock, and then you do that. So basically this is how we do the generation of the signal, the reset logic, and then we count. So then okay, now because this test bench is supposed to work for different sets of different, let's say I would like to test this circuit for an 8-bit input, 8-bit counter, 4-bit counter, or whatever. So instead of hard coding the value here, you can simply say 2 to the power, whatever, you read the value of the width which is given directly inside. Just 1 second. Here, you read the width, you get it directly. So with just this, you get this part, and then we enable the enable port, and then we start counting for count equal to. So do for each one of these, we allow the system to go 1 clock. At the end of 1 clock, we wait until we get the rising edge of the clock. Then we read the output of the dut.count, which is the name I've given here, as you can see. Where is it? This part, count. So we read the count. We compare it with the true count. What's the true count? The true count is going to be the count that we get here, and then you do the modulus operation, so that because as you might expect, the true count will increment, and then it will reset. Like let's say for 4-bit you have 1 1 1 1, it will reset to 0 0 0 0, and so on. And then you basically print out, if you want to print out to see what's going on during the test, and then you say this is basically how you tell CocoTB to know whether there has been a problem. I mean, there has been a mismatch between what you expect and what the circuit is producing, and then it gives you something like that. So easy. So this is basically a test bench, one test bench. Now, so this is the test. Now let me show you the other part. So this is the part now where you want to simulate the test bench. So here I set stuff like the simulator. What's the top level language is Verilog. What's my time scale? This is the name of the Verilog sources. Top level design, I only have one guy, so that's the name I design. The module that I'm testing, remember this is the test that I wrote my test bench. Then whether you want the system to generate for you waves, you know, the sort of waves that you see like 0, 1, 0, 1 or something like that. Now here is, I set all of these things as you can see here. And then this is the part now which probably you can test for different types of parameters. So here we have a default parameter of 8, so an 8-bit counter. Now you can say, let's say you have more than one parameter, you have a bunch of them. So you would like to test the circuit for different ones. Let's say you come, let's say for a width of 8, for a width, so you can see each one of these in its own dictionary represent a set of parameters for which this code will run once. So if since I have only one parameter, let's say I want to test it for 8-bit and 4-bit, I will put them separately into their own dictionaries. If I had more than one parameter, I would put each of them inside, each of them that needs to change inside here, and then comma, blah, 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 blah. So for each one of these, this guy will run once. And then it will save each of these results in its own special folder so that things are not overwritten. Anyway, this is a very, very long way. Probably I haven't explained it the best way, but this is super simple to do. Let me maybe show you an example so that we can at least appreciate what we're doing here. So this is the counter. Again, so this is the design file that we have, the counter file, the system Verilog. This is the test file which implements how the test is supposed to be done. And then this is the test file which specifies this is a Verilog file and all these sorts of things. So the way you do it is something like this. So the way you do it is you run pytest and then you call that file and then you save the log or something like that. So just like that, I'll do something like this, run. Okay, I have some problem. Let's see where the problem is. CocoTB, my design. Okay, I have nothing called my design. Okay, for whatever reason, this guy is called my design. I have no idea why. Let's say my design. I have no idea how it changed. Really, no idea. Let's do one more time. Okay. So this is the simulation has run. Let me go through this part. So this is the part which, okay. This looks like junk a bit, but let's focus here. So we can see from the print statement that I had here. Let me just show you. So this print statement that I was seeing here, that when the clock is 1, this is the output of the circuit. So as you can see, when the clock was 1, I had 0, 0. So this is for the 8-bit case. As you can see, it's yeah, it's running as you expect. And then for 8-bit, we go all the way to 2 to the power 8, which is 256. And then I added one extra one so that we can see that it's actually reinitializing to 0, 0, 0, 0. So this, you can see the status is test passed. I only have one test and whatever. And then for the second one, which is the 4-bit case, as you can see, it has only 16 inputs and then plus one extra stuff. So let's say let's deliberately do a mistake. So instead of plus, we do a minus, let's say. Just so a mistake in the code. Then I can do something like this. I do something like that. Okay, now I have an error. So you can see the problems where things failed. So you can see, have a look here. So so it tells you that this part, assert 1, which means that after the first clock pulse, we were expecting to have 1. But however, the result that we got is 1, 1, 1, 1. So 1, 1, 1, 1 is not 1. This is the problem. Again, similarly for this other guy, same problem, of course. But anyway, you get the point. So this is how you test your circuit. You make sure that you define a well set of input-output pairs, and then you test. No need to look at how do you call them, waveforms, all of these sorts of things. You just make sure that everything works nicely. So this is how I test the circuit. So these are the simulation files that for the different tests that we have. So these are the output of the test using the iVerilog, the Icarus Verilog simulator. Let me just show you quickly. So this is the waveforms that we had dumped. Remember, there was this thing called one of the options that I said waves true. So it dumps it for you. So let's say open it with GTK wave. We can see the design here. So these are all of the stuff that if you want to get a closer look at what's going on inside, append, and then you can do this. So this is the yeah, so this is the case where things failed, I think. Okay, I mean, this is not a good example, so just let me do another one, at least to satisfy the... Okay, now let's reload this. So now we see all of the waveforms that we are supposed to have. Anyway, you get the point. So you can do something like this, and then if you need to look at the waveform, of course, at some point in time, let's say you have some catastrophic problems, you have to look at the waveforms to have an idea where things might be going wrong. But of course, at the same time, you can also print out values as you would debug any normal software. Because at the end of the day, in normal software, it's just like a function. You give it an input, it gives you an output, and then you debug it. So if you have the way of easily writing print statements, all sorts of things, probably you don't even need to look at the waveform plot. Anyway, so this is the, how do you call it, the CocoTB, some example. Maybe let me just show you a slightly different example. So this is a priority encoder. So just have a look here, the priority encoder. So this is basically how priority encoder looks. So basically it takes a string of zeros where there's only one somewhere, and then it encodes that for you into a binary number. That's it basically. So this is basically how you go about testing it, something like this. Again, you have this thing called a test. You write your test and then you feed it your input output. So basically this is where I'm generating my my input output tests. So basically I just generate a huge, so I will receive zeros and ones. So basically I have, this is the number of inputs that so this is an encoder with 16 inputs and 4 outputs. And then I want to test it for 2 different cases, a case where there's only a single bit in the entire string, which is 1. There's only a single bit, which is 1, and another case where it might be possible to have more than 1. You get the point. So again, you just write with all of your skills that you have in Python to generate good input-output pairs for generic case, and then you start just running simulations if you need. So basically, this is how I do my tests inside of I do my tests with CocoTB. Now let me show you something else. Now we've written, we know how to write a code, we know how to do linting, we know how to do simulation. Synthesis, it means that sometimes you write your code, it synthesizes nicely. It simulates nicely, the functionality is as expected, but then the synthesis, it fails, which means that the code that you've written is actually functionally correct, but cannot be implemented in hardware. So I have to be honest with you, I actually don't use Yosis that much, because whenever I want to do the synthesis, I just go to the, if I'm using an FPGA, I just use the Xilinx or whatever. If I'm doing ASICs, I just use a Genos or a design compiler from Synopsys, and then do that. But it's nice to have, but I don't have access, let's say, to these tools, because these are located in the server of, these are like super expensive tools. They're located in the server. I don't have them on my computer, whereas Yosis is free synthesis tool, and you can at least get a first-hand look into whether your code is synthesizable or not. So let me just show you very, very, very simple example. Again, the point of all of these demonstration is not to overwhelm you with things that are not important. Like, who cares if I am showing you a very difficult design? The point is, you have a very simple design like a MOX. Who cares about how a MOX looks like? It's simple. Everybody knows how a MOX looks like. And how can we synthesize this? Let's say we want to synthesize this. So let me just show you quickly. So with Yosis, you also write a script. Let's say you basically read the Verilog file, you elaborate, And then if you would like to see a representation of how your circuit looks like, let's say you want to see, okay, this is how my the blocks are connected, and then you want to actually how do you say, optimize, and you want to translate so you want to go, like when you have like things like VHDL or Verilog, you have processes. Inside these processes you have things like if then statement, case statements. Usually so this command will say try to implement what's inside the if statement into things like moxes and all of these sorts of things. Then here we can see the difference between this stage before this translation has gone into it, and then after this stage. And then if you have things like FSMs or whatever, there's a special way to optimize them. And then this part, if you have flip-flops, like whenever you are doing synthesis, you are mapping from a generic set of gates, all of these sorts of things, to the specific stuff that you have in your own library. Let's say you are using this particular technology. Let's say supports 4 input AND gates. So with 4 input AND gates, then if you have any 4 input stuff in your code, then it will be mapped directly to that 4 input AND gate, instead of having to map it into two 2 input AND gates, and then taking the result and ANDing it again. You get the point. So this is where this is the part where you do that thing, the mapping part and all of these sorts of things. Then you want to clean things up, and then start, which will return tell you how many cells you're using, how many OR gates and AND gates and all these sorts of things. And then you write the synthesizable file. This synthesizable file that we write now, you can now take it now into, if you're doing floor planning and all these sorts of things, then it will convert that. It will use this information to generate for you the how do you call it, the floor plan, not floor plan, what's it called, the place and route and things like that. I just can't remember the word right now. So anyway, let me just show you how this is done. It's very simple. So you just put your CS and then you run the script, and then just like that, bang. So basically we're done. So it tells me that this, of course, when it reaches this stage, it means that the design is synthesizable and all these sorts of things. So we're using how many, of course, there's no this is a purely combinatorial circuit, so there's no need for memories and all sorts of things. We have, this is very simple. It's very boring, but you get the point. It's just using single mux. Let's have a look here at what we have. So this is basically the first guy who, let's go to probably it's better if you just see here, just so that we see these things side by side. So notice here, inside here, we are saying if select equal to 1, then do this, else do that. So this is the part of the code. So it checks if select equal to 1, if true, then it runs the process and whatever. So, but right now it has not yet translated what is inside the process into actual stuff that can be mapped into one of the things inside your Liberty file. So this is the part which comes, as I said, after that second stage, where we can see now. So this is the part now where where we have exploded the process. As you can see now, it has actually mapped what's inside the process directly into a mux. So this thing we see here was before we tell it to optimize the processes. You can see it has a separate block for the equality and another thing for something else. And now it decides, okay, equality and branching between two different things is basically a mux. So it has replaced it with the mux. So if you have a simple design, all these sorts of things, yes, you can actually just cross-check, have a look at how the code, the high-level view of the code and all of these sorts of things. It's very intuitive and whatever. So I guess this is this is the end of this video, and then I hope probably you have learned something, and then maybe if you if you find some of these things useful, let's say for some whatever reason you decide to use Neovim to do your typing, and then you want to try the snippet engine, I can always, of course, share my my code online, then probably you can use them. I guess that's it.